Week 11, problem 6. Consider a bright star in our night sky. Assume its distance from Earth is 70 light years, and its power output is 4 times 10 to the 28th watts, about 100 times that of our sun. Find the intensity of the starlight at Earth. All right, so intensity is power per square meter. They're giving us power already with our watts. So what we got to do is we got to find out how much. All right, got it. So I'm going to start by drawing a picture, which is almost redundant at this point because that's pretty much what I always do. It's not. I say it as if it's new. So get some different color. There we go. So that right there, that's an arrow. It's going to be the star. That is going to be a sphere. I know it's two-dimensional, but pretend it's three-dimensional. And the surface area of that is going to be 4 pi r squared. And the idea here is 70 light years. You have all this power from the star, and it goes outwards uniformly in all directions, and it dissipates as it goes. Maybe dissipates isn't quite. I think it's called spreading. It's basically a type of attenuation. It gets weaker because it's farther away. Bam. Not hard. Not hard. Okay. So now we need to find the area of that sphere, the surface area of that sphere. So 4 pi r squared is the formula for a sphere's surface area. But you can see that my confidence is waning, so I'm going to look this guy up just to be safe. Bam. Area equals 4 pi r squared. Okay? So the way we convert light years into normal like units of measure, like meters, which is what we want here, is we do that through, we take its, so we have, let's see, light, so we have 70 light years, which is the distance that light travels in, so velocity equals distance divided by time. Therefore, distance equals velocity times time. So this is, this is not supposed to be hard. 70 times 3 times 10 to the 8th meters per second times 1 year. There we go. So now what we have to do is we got to convert this year into seconds. And normally, there's a year to seconds. Converts. What is 1 year in seconds? So it's like pi times 10 to the 7th or something. Yeah, right there. 3.154. So we got 3.154 times 10 to the 7th seconds per 1 year. Years cancel, and we're left with just meters. Seconds cancel. All right. So we're going to do 70 times 3 times 3.154 times 10 to the 15th. I think that's 15th. 8 plus 7, 15. Yep. And that gives us, a giant number. What? Why didn't you? No? I want some scientific notation here. Why aren't you giving me scientific notation? Well, okay. 6.6 times 10 to the 17th. Okay, I'm good with that. So we have 6.6 times 10 to the 17th. And that's meters. That is the radius of our sphere that we just created here. All right? So now we need to convert that 4 times pi times this giant thing squared. That is going to give us the surface area. And now we're going to take the power and divide that by the surface area. So 4 times 10 to the 28th. Good thing that's a big number. All right, probably get something small. Yep, very, very small. So I have 4 times 10 to the 28th, or 4 pi times 10 to this giant thing squared, and we get 7.23 times 10 to the negative 9th. So intensity equals 7.26. 7.26 times 10 to the negative 9th. And do they want it in nano? They did. Actually, that actually worked out well. So it was 7.26. Nanowatts per square meter. All right, now to backtrack real quick. Intensity, as you can see through dimensional analysis right here, intensity equals power over area. So we did is they already gave us the power, and the big thing was just converting the light years to a radius, which gave us meters. We then took that meters, we used the surface area of a sphere, 4 pi r squared, converted that into a total surface area, and we found out if we evenly distributed that power, how much power would be in each square meter. And the answer is not a lot. Very small. Find the power of the starlight the Earth intercepts. 1 year is the distance traveled by the light through a vacuum. 1 light year is the distance traveled through a vacuum. The radius of the Earth is 6.37 times 10 to the 6th. Okay. So now they're saying, how many square meters is the Earth? But they're not asking like normal square meters, not like the surface area of the Earth. They're asking for, so we have a Earth that looks like this, and maybe add a little shading. That way you can, oh my gosh, that is so terrible. All the actual artistic people out there are like, it's terrible. They're just cringing. I'm just going to delete the rest of that. Okay, so pretend it's a sphere. And what we want to find out is if we have light coming this way, how much is intercepted. So we're not actually going to use the surface area of the Earth, but we're going to use like a circle. We're going to use the area of the circle around the Earth, through the Earth. Basically, like if you're shining light here and you had a wall over here, what would the shadow look like? Well, the shadow would look like a circle, and that's what we're going for here. The light would be warmest right here. It'd be coolest up here. But we'd get the when you sum up all the light, how much energy is intercepted by the Earth. That's where we're going with that. All right. So we have our 7.26 times 10 to the negative 9th. This will be watts per square meter. And we want to find out how many watts do we get. Find the power. Yep, watts. So we're going to take 7.26 times 10 to the negative 9th watts per meter times pi r squared. That's the area of a circle. Area of a circle is pi r squared, and this radius is going to be the Earth's, times pi times 6.37 times 10 to the 6th squared. Alright, so let's see here. Maybe if I just click this number, it'll go up there. Yes! And now that looks times pi times 6.37 times pi times 6.37 times 10 to the 6th squared. Alright, let's see what this says. So I had this giant number times 6.37 squared Yeah, probably. And the pi is supposed to be outside the square. I think it is. Yeah, I'll say it is. Okay, so this is... I want scientific notation. 1, 2, 3, 4, 5. 9.25 times 10 to the 5th equals 9.25 times 10 to the 5th watts, which is actually pretty good. That's pretty good. That's respectable. 1, 2, 3, 4, 5. That's like 925 kilowatts. So that's, yeah, that's good. But they want it in megawatts. All right. So times 10 to the 6th watts per 1 megawatt, which is 0.925 megawatts. Put some units. There we go. Megawatts. All right. Seems good. Yep. It's a little bit more challenging than the previous ones, but still very reasonable. Not too conceptually difficult. All right. On to problem 7.